Changes in matter. How do we describe matter? Make a connection. From apples and grapes to bananas and kiwis, fruit comes in an amazing variety of shapes and colors. How many words can you use to describe how your favorite fruit looks, feels, smells, and tastes? Find out about some physical and chemical properties of matter. Vocabulary: matter, page 4. Physical property, page 4. State of matter, page 6. Chemical property, page 7. Clouds, air, trees, grass, and objects such as houses and fences are all made of matter. Physical properties. Matter makes up all the objects and living things around us. Desks, books, food, air, plants, animals, and people are all made up of matter. What makes one material or substance different from another? All matter is composed of tiny particles called atoms. Atoms are often joined together in units called molecules. The way matter looks or behaves depends on the kinds of atoms it's made of and the way those atoms are joined together. We often identify and describe matter by referring to its physical properties. A physical property is something about matter that can be easily observed with our senses or measured. Size, shape, color, taste, and smell are examples of physical properties. Some materials are rough and hard, while others are smooth and soft. Texture is a physical property that describes how rough or smooth a material is. Hardness is a physical property that describes how easy it is for a material to be scratched by another material. When we say a penny is round or a kitten is gray and white, we are describing physical properties of matter. What other physical properties do you notice about these things? Mass, weight, volume, and density are all physical properties we can measure using different kinds of tools. All matter has mass. Mass describes the amount of matter in an object, which is usually measured with a balance. Weight is related to mass, but they are not the same. Weight is the force of gravity acting on an object. The more mass an object has, the more it weighs. All matter takes up space. Volume describes the amount of space that matter takes up. To calculate the volume of a solid object, such as a block of wood, first measure its length, width, and height with a ruler, then multiply those numbers together. You can determine the volume of a liquid, such as orange juice, by using a measuring cup or graduated cylinder. Imagine a wood block and a brick of the same size. Their volumes are the same. So why does the brick feel heavier than the wood? Brick is denser than wood, so the brick has a greater mass for its volume. Density describes the amount of mass something has compared to its volume. To calculate an object's density, you divide its mass by its volume. A balance can be used to measure and compare the mass of different objects. A measuring cup can be used to measure the volume of a liquid. The volume of the wood block is equal to the volume of the brick, but their masses are different. That's because the density of the brick is greater than the density of the wood. Some materials have the physical property of being magnetic, which means they can be attracted by a magnet or can become magnets. The metals iron, cobalt, and nickel are all magnetic. The metal steel contains iron, so most types of steel are also magnetic. Conductivity is another physical property. A good conductor is a material through which heat or electric charge travels easily. Many metals are good conductors of both heat and electric charge, while materials such as plastic and rubber are not generally good conductors. Most matter around us is found in one of three main forms, or states of matter: solid, liquid, or gas. State of matter is a physical property. Solids have a definite or set volume and shape. For example, the volume and shape of a solid brick do not change. Liquids have a definite volume, but no definite shape. Liquids, such as milk or honey, flow and take the shape of their container. Gases have no definite volume or shape. A gas, such as helium or oxygen, will expand to fill whatever container it holds. Why do the states of matter look and behave differently from one another? Their particles, atoms, or molecules are arranged differently and move differently. Describe some physical properties of this book. Solid. Definite volume and shape. Particles are packed tightly and vibrate only slightly back and forth in place. Liquid. definite volume but no definite shape, flows and takes the shape of its container. Particles are packed loosely and move more freely than in a solid, sliding past one another easily. Gas, no definite volume or shape, expands to fill its container completely. Particles are spaced far apart and move past one another more easily and more quickly than in a liquid or a solid. Compare the particles in the three states of matter, solid, liquid, and gas. How are the particles arranged differently? What is different about their motion? Combustibility, the ability to burn, is a chemical property of certain kinds of matter. Paper is a combustible material. Iron and some forms of steel can rust if they are left outside for too long. The ability to rust is a chemical property of these materials. Chemical properties. In addition to physical properties such as color, texture, mass, volume, density, or state, matter has chemical properties. Chemical properties are very different from physical properties. Chemical properties describe the way matter reacts with other kinds of matter. Changes occur when one substance reacts with another substance. You will learn more about those changes on page 20. Some substances react easily with many other substances. Some substances are more stable and do not react easily with others. Combustibility, the ability to burn, is an important chemical property. When something burns, it reacts with oxygen gas in the air. Paper, wood, wax, and oil are combustible materials. So is sulfur, one of the substances used to make matches. Most metals are not combustible. The ability to rust is another interesting chemical property. The metal iron can rust. When iron rusts, it reacts with oxygen in the presence of water. Materials such as plastic and glass do not rust. Describe one chemical property of this book. Reflect on reading. Before reading, you previewed book features such as photographs and captions. Which feature most helped you understand about properties of matter? Explain how they helped. Apply science concepts. Imagine a brand new candle and write about its physical and chemical properties. Now, imagine that the candle has burned. Are the properties of the candle different from before? Describe them. Build reading skills. How to read diagrams. A diagram is a picture or drawing with labels. It can show how something works or how the parts of something fit together. You will see a diagram on page 13. As you read, think about how the diagram helps you understand the information in the text. Tips. Follow the guidelines when reading a diagram. Read the title of the diagram and look at the pictures to find out what object or event is shown. Read each label and look closely at the part of the diagram it goes with. Follow any arrows or numbers. Read the caption. Explain in your own words what the diagram shows. A good way to understand and remember what a diagram shows is to redraw it yourself. What are physical changes? Make a connection. You can create a beautiful castle using sand on the beach. Explain how the physical properties of the sand change as you build. Do these changes last very long? Find out about physical changes in matter, how matter changes state, types of mixtures. Vocabulary. Physical change, page 10. Change of state, page 11. Melting point, page 11. Boiling point, page 12. Evaporate, page 12. Condense, page 12. Mixture, page 14. Solution, page 15. Solute, page 15. Solvent, page 15. Solubility, page 15. Suspension, page 15. Colloid, page 15. Changes of shape or size. Some physical properties of matter can be changed. Consider some of the things you could do to change a sheet of paper. You could tear it into pieces, cut it into strips, or fold it into a paper airplane. You could roll it into a tube or crumple it into a ball. These actions change the paper's shape and size. Tearing, folding, bending, breaking, squeezing, and cutting are all ways to cause physical changes. In a physical change, the form or the appearance of matter changes, but the matter does not change into a different kind of matter. When people carve stone or wood, they are making a physical change. Shattering a drinking glass also causes a physical change. Can you think of some other ways to cause physical changes in matter? Some physical changes can be reversed. For example, you could mold a ball of clay into a different shape or break it into smaller pieces. Then you could undo those physical changes by squeezing or pressing the clay back into its original shape. The clay may change in shape, but it is still the same substance. What occurs when matter goes through a physical change? Folding paper into the shape of a bird is a physical change. Folding changes what the paper looks like, but not the kind of matter it is. Even if you pull apart a ball of clay and give it a different shape, the clay is still clay. You could reverse this physical change by squeezing the clay back into a ball. Changes of state. If matter is heated or cooled enough, it can change from one state to another. For example, when you spread butter on hot pancakes, the butter melts and changes from a solid to a liquid. A change of state is a physical change. Recall that the atoms or molecules of solids, liquids, and gases move differently. Every object has energy because of the motion of its particles, and that energy is called thermal energy. Thermal energy can be transferred from one object or place to another, and when that occurs, matter may change states. Solid to liquid. Thermal energy flows from warmer objects to cooler objects. When you hold an ice cube, for example, thermal energy from your warm hand moves to the cold ice. This added thermal energy causes the molecules in the ice to move faster, and its temperature rises. After a while, the molecules move so fast that the ice can no longer stay solid. The solid ice reaches its melting point and begins to change to a liquid. Liquid to solid. If you place the liquid water in a freezer, it will become solid again. Thermal energy from the water moves to the cold air in the freezer. After a while, the water molecules move so slowly that the water can no longer stay liquid. It begins to freeze and change to a solid ice. When solid ice is heated, its molecules speed up. The ice begins to melt and become liquid water. When liquid water is cooled, its molecules slow down. The water begins to freeze and become solid ice. Butter has a higher melting point, about 35 degrees Celsius or 95 degrees Fahrenheit, than ice does, 0 degrees Celsius or 32 degrees Fahrenheit. Butter is solid at room temperature, but it melts on top of hot pancakes. When water reaches its boiling point, it quickly begins to change from a liquid to a gas. You can observe bubbles of gas in the liquid. Different substances have different melting and boiling points. Melting and boiling points. Substance, aluminum, melting point, 660 degrees Celsius or 1,220 degrees Fahrenheit. Boiling point, 2,519 degrees Celsius or 4,566 degrees Fahrenheit. Iron, 1,538 degrees Celsius, 2,800 degrees Fahrenheit. 2,861 degrees Celsius, 5,182 degrees Fahrenheit. Mercury, negative 39 degrees Celsius, negative 38 degrees Fahrenheit. 357 degrees Celsius, 675 degrees Fahrenheit. Water, 0 degrees Celsius, 32 degrees Fahrenheit. 100 degrees Celsius, 212 degrees Fahrenheit. Nitrogen, negative 210 degrees Celsius, negative 346 degrees Fahrenheit. Negative 196 degrees Celsius, negative 321 degrees Fahrenheit. Oxygen, negative 219 degrees Celsius, negative 362 degrees Fahrenheit. Negative 183 degrees Celsius, negative 297 degrees Fahrenheit. Liquid to gas. Matter also can change from liquid to gas. If you heat a pot of water on a stove, the thermal energy in the water increases and its temperature rises. Soon, the water molecules begin to move so fast that the water cannot stay liquid. Gas bubbles form throughout the liquid. The water has reached its boiling point and begins to change to water vapor, which is a gas. When a liquid turns to a gas, scientists say it vaporizes. Sometimes a liquid vaporizes at a temperature below its boiling point. The liquid evaporates. This occurs, for example, when a puddle dries up. Some water molecules at the surface of the puddle have enough energy to change to water vapor. Over time, the whole puddle evaporates. Gas to liquid. When water vapor in the air cools, it turns to liquid. Have you ever noticed water droplets on the outside of a cold glass of lemonade? Water vapor in the air cools when it touches the cold surface of the glass. Soon, the molecules of water vapor slow down so much that the gas condenses or changes to liquid, forming water droplets on the outside of the glass. A cold glass cools the water vapor in the air around it. The water vapor condenses, changing from a gas to a liquid. You can observe the droplets of liquid water, that form on the outside of the glass. Water changing state. Water is the only substance that exists naturally on Earth in all three states of matter: solid, liquid, and gas. Let's summarize how water states change. If you heat solid water, or ice, you are adding thermal energy. The ice's molecules move more quickly and its temperature increases. The ice melts and becomes liquid water. If the liquid water gains more thermal energy, it boils and turns to water vapor, a gas. If you cool water vapor, the gas form of water, you are removing thermal energy. The water vapor's molecules move more slowly and its temperature decreases. The gas condenses and becomes liquid water. If the liquid water loses more thermal energy, it freezes and turns to solid ice. Explain what causes matter to change from one state to another. How water changes state. Ice melting, water boiling, water vapor condensing, water freezing, solid, liquid, gas. Adding thermal energy can cause melting or boiling, while removing thermal energy can cause condensing or freezing. A tossed salad is an example of a mixture. Even though the ingredients are mixed together, they are still the same kinds of matter they were before they were mixed. Mixtures can contain matter in different states. Your breakfast bowl might contain solid cereal and raisins mixed with liquid milk. Mixtures. Types of mixtures. A mixture is composed of two or more kinds of matter that have been mixed together. A tossed salad, for example, is a mixture of lettuce, tomatoes, and dressing. Making the mixture is a type of physical change because the materials that are mixed do not change into different materials. The lettuce in a salad is still lettuce, even after it has been mixed with other ingredients. Two mixtures may include the same ingredients, but in different amounts. For example, one tossed salad may have more tomatoes than another. Both salads are mixtures, but they are not exactly the same. Some mixtures contain ingredients in the same state of matter, while other mixtures contain ingredients in different states. One type of salad dressing is a mixture of two liquids, oil and vinegar, with some solid spices. Air is a mixture of nitrogen, oxygen, water vapor, and other gases. Soil is a mixture of rock pieces, plant and animal material, air, and water. Fizzy soda water is a mixture of liquid water and carbon dioxide gas. A mixture that contains a metal is called an alloy. Brass is an alloy composed of copper and zinc. Most alloys are made for their special properties such as hardness or strength. Brass is a mixture of metals. It is soft enough to be shaped into useful objects such as musical instruments and doorknobs. Solutions. A solution is a type of mixture in which one substance is mixed evenly throughout another substance. A solution looks as if it is made of only one substance, even though it has two or more substances in it. If you stir salt into water, The salt dissolves or spreads evenly throughout the water. In the salt water solution, salt is the solute, or the substance that dissolves. Water is the solvent, or the substance in which the solute dissolves. Salt has a high solubility, or ability to dissolve in water. Solubility is a physical property. If you keep stirring salt into a glass of water, you will reach a point when no more salt can be dissolved, and the solution is called saturated. Suspensions. A suspension is a type of mixture in which the substances do not mix evenly together. Particles of one substance are suspended in or floating throughout another substance. Unlike solutions, suspensions do not stay mixed, and the suspended particles soon fall to the bottom of the container. Oil and vinegar salad dressing, muddy water, and orange juice are suspensions. Colloids. A property of a colloid are between those of a solution and a suspension. The particles in a colloid do not dissolve, yet they tend to stay mixed. Milk, toothpaste, and paint are colloids. Oil and vinegar salad dressing is a suspension that does not stay mixed for very long. The vinegar and spices soon sink to the bottom. When salt is stirred into water, the resulting mixture is a solution. The salt and water are mixed evenly, so you can't see the salt, but it is still there. Paint is a colloid. Tiny particles of color called pigment are mixed in a liquid. The pigment does not dissolve, but it still stays mixed. Separating mixtures. The ingredients in most mixtures can be separated from one another. However, some mixtures are more difficult to separate than others. The method you choose to separate a mixture depends on the properties of the ingredients. Some mixtures can be separated simply by sorting the parts. Suppose you have a fruit salad but do not like blueberries. The different fruits are easy to recognize by their colors and shapes, so you could pick out the blueberries. Strainers, screens, and filters are often used to separate mixtures of liquids and solids or mixtures that have different sized pieces. Suppose you want to separate a mixture of boiling water and spaghetti. Since the pieces of spaghetti are large, you could pour the mixture through a strainer or colander. The boiling water easily passes through the small holes of the strainer, leaving the spaghetti behind. Archaeologists working at dig sites sometimes use special wire mesh screens. They use them to carefully separate soil mixtures, looking for pieces of pottery, bone, or other objects. How would you separate this fruit salad mixture? Most mixtures can be separated based on the physical properties of their ingredients. Spaghetti can be separated from water using a strainer or colander. To separate a mixture that contains pieces of many different sizes, you can use more than one screen. A screen with large holes is used first, followed by screens with smaller and smaller holes. Magnets can be used to separate mixtures that contain magnetic metals such as iron or steel. Recycling plants often have piles of mixed scrap metal that they need to separate and sort. Huge magnets are used to pull the iron or steel scraps away from the other metals, such as aluminum. Evaporation or boiling can be used to separate some solutions. Suppose you have a solution of salt and water. You could set the container of salty water on the counter and wait until the water evaporates, or you could set it on a burner or hot plate and let it boil. Once the water has evaporated or boiled away, solid salt will be left behind. Sometimes many steps are necessary to separate a mixture. Consider how you might separate a mixture of salt and sand. First, you could add water and dissolve all the salt because salt is soluble in water. Next, you could use a filter to separate the sand from the salt water. Finally, you could let the water evaporate, leaving the salt behind. Explain why making a mixture is an example of a physical change. At this recycling plant, steel cans are separated from aluminum cans by an enormous magnet. Objects made of steel are attracted to metals, but objects made of aluminum are not. Reflect on reading. Think of an example of water changing state in nature. Draw and label a diagram of this change. Add arrows to represent thermal energy and show the direction of its movement. Apply science concepts. Imagine ice cream melting on a hot summer day. Which properties of the ice cream change as it melts? Which properties stay the same? Build reading skills. Main idea and details. The main idea of a paragraph or section of text is the most important point. Details are facts that support or give more information about the main idea. As you read this section, try to identify the main ideas about chemical changes and how to recognize them. Tips. The main idea of a paragraph is stated in the topic sentence. The topic sentence is often the first sentence in the paragraph. To find the main idea, ask, what is the most important point to know about this topic? Details may answer who, what, where, when, why, and how questions about the topic. Details may include examples, descriptions, explanations or reasons, additional facts. A concept web can help you organize your thoughts about the main idea and details. What are chemical changes? Make a connection. Consider the properties of a raw pizza. In what ways is a pizza different after it has been baked in a hot oven? Why do you think this occurs? Find out about chemical changes in matter, recognizing chemical changes. What happens to the mass of matter during chemical or physical changes? Vocabulary, chemical change, page 20. Recognizing chemical changes. During a physical change, a substance may change form or state, but it does not change into a completely new substance. Chemical changes are very different from physical changes. Recall that the chemical properties of a substance describe how it reacts to other substances. In a chemical change, the substances react with one another and new substances are formed. When iron in a nail reacts with oxygen gas in the air, a new substance called rust is produced. A burning log reacts with oxygen, producing ashes, smoke, and hot gases. The new substance produced by a chemical change have properties that are different from those of the original substances. This is because the atoms in the original substances have rearranged and are now joined together in new ways. Baking and cooking often involve chemical changes. When we bake dough, it changes color, hardens, and becomes bread. The bread is a new substance that is produced when substances in the dough react as it bakes. Think about frying an egg, grilling a burger, or steaming some vegetables. In all these examples, chemical change occurs as the raw food becomes cooked food. Before baking, after baking. Making bread from dough involves chemical changes. Reactions that take place during baking give bread its color and flavor. This decaying apple is going through a chemical change. It is reacting with oxygen in the air to produce new substances that are different from the substances in the fresh apple. Chemical changes also occur in your body when you eat and digest food. Chemicals in your digestive system react with food. They break it down into substances your body can use for energy and growth. If you slice an apple and leave it on the counter, the fruit will begin to decay. It will turn brown and begin to smell. These changes occur when the apple reacts with oxygen in the air. The Statue of Liberty was a gift to the United States from the people of France in 1886. Its copper surface was originally a shiny reddish-orange color. Over many years, the metal has become tarnished because copper reacted with oxygen and salts in the air. The green substance that was produced is called a patina. Chemical changes are sometimes called chemical reactions. The substances that react are called reactants. The new substances that are produced by the reaction are called products. For example, when a chemical reaction takes place between the gases hydrogen and oxygen, water is produced. Hydrogen and oxygen are reactants and water is the product. The product is very different from the reactants. The Statue of Liberty's green color is the result of a chemical reaction between the copper statue and the oxygen and salts in the air. Signs of a chemical change: color and odor change, new substance present, gas bubbles produced, light, sound, and heat produced. Sign: color changes. Examples: baking bread, decaying food. New substance present: rust, smoke. Odor changes: burning toast, decaying food, decaying leaves. Gas bubbles produced: vinegar and baking soda. Light, sound, or heat produced: fireworks, burning match. How can you determine if a chemical reaction has occurred? Look for these signs. Certain signs are evidence or clues that a chemical change may have occurred. A change in color is one sign of chemical change. Bread dough has a different color after it has been baked, and an apple changes color as it decays. Both of these are examples of chemical changes. If you observe a new substance forming, that's a sign of a chemical change. That's a sign that a chemical change may be occurring. Brownish red rust coating the surface of a metal object is evidence of a chemical change, so it is the smoke that appears during a campfire. A new odor or smell is another sign of a chemical change. The smells of toast burning or food decaying are evidence that chemical reactions are occurring. Bubbles are another clue that a chemical change has taken place. For example, when vinegar is added to baking soda, bubbles appear. The bubbles are evidence that something different, the gas carbon dioxide, has been produced. Sometimes chemical changes produce light, sound, or heat. The bright flash and loud boom of fireworks are evidence that the explosions are chemical reactions. The light and heat produced by a burning match are also clues that a chemical change is occurring. Give 2 examples of chemical changes. What occurs during a chemical change? Matter, mass, and change. Sometimes when substances react, it seems as if nothing is left behind. As a campfire burns, the logs seem to disappear. However, matter is neither lost nor gained. It is only changed. In both chemical and physical changes, the total mass involved always remains the same. What happens to the matter in the campfire logs? As the wood burns, it combines with oxygen from the air to produce ashes, smoke, and gases. The mass of the ashes, smoke, and gases equals the mass of the original wood and the oxygen. The total mass of the reactants in the beginning of a chemical reaction equals the total mass of the product at the end. The amount of matter stays the same during a physical change too. Suppose you have an ice cube in a sealed container and you measure its mass. After a few hours, the ice cube has melted, yet the mass is the same. Even though the matter changed from a solid to a liquid state, the amount of matter did not change. What effect does a chemical or physical change have on the mass of the matter involved? When a campfire log burns, matter may seem to disappear, but it really does not. The total mass of the ashes, smoke, and gases produced equals the mass of the original logs and the oxygen used by the fire. Reflect on reading. Create a concept web like the one on page 18 to organize information about how matter can change chemically. Write the main idea about chemical changes in the center, then add some details and examples. Apply science concepts. Look for evidence of chemical changes in your everyday life. In your science notebook, record all of the chemical changes you observe for one full day. Glossary. You may press pause here to read any of the definitions of the terms found in the glossary.